In part one of this introduction to the Arduino, we went over the hardware itself and created a very simple circuit with a single LED that is going to be controlled by a single push button, and put that circuit together on a physical breadboard. I was going to begin this by having you download and install the software, but realized that some of you may not have your Arduinos yet. So instead, I'm going to introduce you to some nice browser-based design and simulation software that I've used quite a bit. So, if you go to tinkercad.com and sign up for an account, you can join now with any number of sign-up options, a specific email or Gmail or an Xbox account or a Facebook account. I already have a personal account that I initially set up when I was looking for easy design software for my 3D printer. Originally, Tinkercad was just 3D design software. It didn't have anything electronic whatsoever. So if you needed to quickly do something simple, like, for example, making a block and putting a couple of holes in it, and maybe putting a cone on top. You could extremely quickly, with very little time spent learning the interface, create 3D designs. And then once you were ready to print them, click export, send it out as an object file or an STL file or GLTF file or an SVG if you want to do some laser cutting. And if you haven't done much mechanical design or 3D design, maybe you're coming from a computer programming course or an electronics course and you haven't done much mechanically, this is actually a pretty fun place to start. That's as much as I'm going to show you for now. What we're interested in is circuits. So from circuits, you can quickly create a new circuit, and it starts off with your standard blank canvas, and on the right, a library of components that you can drop into that blank canvas and connect together. So we're just going to recreate what we did in hardware in the first section by grabbing an Arduino and grabbing a breadboard and zooming to make everything fit. We're going to grab a resistor, and right click on the resistor, bring up the resistor, and it is a 10K resistor. You can choose the units here. You can also name it here if you wanted to, but it's not really necessary. We're going to grab an LED. The long leg is the anode, which is the positive leg, so we want that to be connected to the Arduino. You can choose what color, and you can change back and forth between colors all you want. We can also call this LED 1 or floor 4. It doesn't really matter. We're going to connect the resistor to pin 12, which is going to be our digital output. And if you move things around after you've dropped it on the workspace, you know, the wires and connections will just stretch with you. We're going to grab a push button, and that push button is going to be connected to input 11. The other side of the push button is going to be connected to the positive rail, and the Cathode of the LED will be connected to the negative rail. We'll grab the 5 volts from the Arduino and connect it to the nearby positive rail. We'll grab the ground pin and connect it to the negative rail. And I want that actually to move over one, so we can just drag and drop the connection point. And then a jumper from the negative rail to the opposite negative rail, which completes the circuit for the LED. And that's it. We have a fully functioning circuit in the simulator for an Arduino, just waiting for code. When you select code, the first thing that's going to come up is the default option, which is code blocks. It's very simple, drag and drop, similar to Scratch, if you have an experience with that. But we are going to program this not in drag and drop blocks, but a text editor in the C++ variant that Arduino is programmed by. And let's just zoom to fit again to get this out of the way. Before we go on, you can also color code things. So just like with the original physical circuit, I can color code the positive wire to be red, the negative wire to be black. Just to keep things organized in our brains. So now anything that's connected directly to the positive supply is red, and anything connected to the negative supply directly is black, and we're using different colors for everything else. By default, every Arduino that you purchase will come with a program running on it that blinks the LED on board that's connected to pin 13. We can easily test the simulator just by running this program by clicking on Start Simulation. And looking at the simulator, we can see that the onboard LED that's connected to pin 13 is in fact blinking on and off once a second. We're going to stop the simulation here and erase the default program and build things up from scratch. And I'm going to change the default random 2-word name of the project to something that makes sense, more sense than Frantic Jacob. So we just click Intro to Arduino PV and LED. You'll notice all changes are saved here. Anytime you make a change to your program, anytime you make a change to the wiring, it will very quickly update the saved project, and as long as all changes are saved is seen here, you are free to close your browser or just go back to the project space and move on to other things. Just like in any other program, where if you're working on an Excel sheet or a document and you want to save a revision, the easiest way to do that is just to duplicate what you've done when you're happy with it, which will make a copy of the program, well, a copy of the project, and open the copy of the project in a new window. All changes are saved. We can go back. If we open our project, we want to tinker it, and we want to add some first code. Before we start adding code, there's a little tiny bit of what the heck is this? So what the heck is this? This is the default code that you will always be staring at whenever you start an empty Arduino program. In short, any code that you put in this function called setup will be executed once at the beginning of runtime. So when you first apply power, when you first download the program, or if you click the red reset button on the board, it will stop everything, do some cleanup, and run the code that's in setup. But only once. Once the setup code has been executed, then execution passes to the function called loop. And it stays there, cycling over and over and over again as fast as possible until you cycle power or give it a new program or press the reset button again. As a rule, when a person is initially learning how to program, there is a hello world example to follow. If you're programming on a computer, normally that takes the form of actually printing the words hello world, but we're going to do something a little bit more hardware specific. Since it's an Arduino, our version of the hello world program is blinking an LED. Because that's the whole point of the Arduino, is to be able to control something based on inputs and code and decision making that happens in the program. So we're going to start off by doing nothing more exciting than turning on the LED and leaving it on. We can do that since it's not something that necessarily needs to happen over and over and over again. We can do that right in setup. Now the first step, as you may recall, is to tell the Arduino that one of these I/O pins is being used as an output to enable the internal transistors that will connect that pin to 5 volts or 0 volts under our program's control. We do that with a function called pin mode with a capital M. Open some brackets, and we tell it what pin we're referring to. In the case of our program, our pin is 12. 12 controls the LED. So we're going to change the mode of pin 12 to be an output. Close the bracket and add a semicolon to the end of your instruction. Now this all by itself is a valid program because we have configured a pin to be an output instead of an input. If we send this out to the Arduino right now, it will do something. We just won't see what it does. Because initially when you change the mode of a pin to an output, it starts off low. It starts off with the NPN transistor connecting it to ground. So our LED will not actually turn on. The next step is turning on the LED. And we do that by telling the Arduino that we want to turn off the transistor that's connecting the pin to ground and turn on the transistor that connects the pin to 5 volts, which will then supply the LED. We do that with the function digital write, because we are writing a value to a digital pin. Digital write, capital W. What pin are we changing the state of? 12. The pin is already low because it's connected to ground. The opposite is connecting it to 5 volts, which is high, in all capitals again. This by itself is also a valid program and actually does something. So if you watch the blue LED while I click simulate, this program configures the pin 12 as an output and connects pin 12 to the high side, which is 5 volts. So let's stop the simulation and turn on the LED for 1 second before turning it off again. Delay 1000 milliseconds, add a semicolon to the end of your command, and write to the digital pin a logic low. Watch the LED, simulate, LED turns on, waits 1 second, turns off. And because this code is in setup, which only runs each command once, it turns it on, waits 1 second, turns it off, and then sits there doing nothing forever. We're almost there. Because what we want is for the LED to flash. So in order to make the LED flash, we need an on time and an off time. And we need it to loop and do it again and again and again. The easiest way to do that is to leave the configuration of the pin in setup and paste turning on and delaying 1 second and turning off and delaying 1 more second before turning it on again into the loop function. Poof. Simple as that. Now, because this is a computer program, and because the classic Hello World program prints something to the computer screen, we're going to add that functionality right now, because later on it's going to be very handy for diagnostics and status updates and just to make your elevator program much nicer to look at. Stop the simulation, and just like configuring pin 12 to be an output being in setup, we are going to initialize the serial communications between the Arduino and the computer in setup. It only needs to happen once, so we put it in setup. Capital S, serial, is the library name. A library is a collection of functions. The serial library has a function called begin. And when you begin, which is initializing serial communications, you also have to tell it what the port speed is. Many devices will come configured at 9600 baud, 9600 bits per second. I typically go faster than that, not super fast, but fast enough to do everything that I need to do at 115,200 bits per second. So now that we've told the Arduino that pin 12 is going to be an output, and we've told the Arduino that we're going to use the serial library to communicate with the computer, let's actually communicate with the computer. So at the same time that we turn the LED on, we can print a message to the user. Serial library dot print. Open bracket, and what do we want to print? LED on. And then after 1 second, when we're turning off the LED, serial.print LED off. Simulate. Now at the moment it doesn't look any different because you haven't seen the serial monitor yet. At the bottom of your screen, over on the right side, if you click the serial monitor, you will now see the output of this program. In the serial library, the print command prints whatever's in the brackets. It might be a number, it might be text, it might be a variable. Whatever is inside the brackets, it prints to the serial console. And then sits on the same line and waits for the next thing to come. We don't really want it to stay on the same line. We want a new line after each print. So we want LED on and go down to the next line. LED off and go down to the next line. We do that by using print ln for print line. We can also keep track of things. For example, we can keep track of the number of times it's gone through this loop. So let's declare a variable, a little container that can hold the number. So we're going to make an integer which takes up 16 bits of the Arduino's memory. Int. We name the variable. I'm going to call it loop count. And although we don't have to do this, it's generally good practice to initialize the variable to a value that makes sense. So our integer, called loop count, is initially going to be equal to 0. Semicolon. At the end of loop, we're going to print the number of times it has gone through the loop. And by the time it's gotten to serial.println loop count, it has in fact gone through the loop once. So let's increment loop count by 1 before we print it. Now let's put all of these print statements on one line for each loop through the program. So I'm going to want to go into the loop and print LED on, but not go to the next line immediately. So we're just going to use print LED on. I'm going to add a dash to that print because I know that something's going to come after. What's going to come after is LED off, and I just don't want the L for the LED off to be right after the ON from light on. After printing LED on in the dash and turning on the LED and waiting 1 second, I want it to print LED off on the same line. And I also don't want this to automatically go to the next line because I want the number to follow. And I'm going to add another spacer to that because I know that the number, the loop count, is going to be printed afterwards. But then after loop count, the number, has been printed, I do actually want to do a carriage return and go to the next line for the next time through the loop. So I will keep the print line for that last print statement. If we run it, we see what's different. And although the timing is a little derpy, I'm okay with this. If you want to play with it, you can certainly play with it. It's a simulator, so the worst thing that can possibly happen is that you crash the simulator and restart the browser tab. Before you start playing though, and before we wrap up this section, I'm going to just clean up this program a little bit and make it easier to read. And we're going to do that in two ways. One is, we can add a comment to our program by adding 2 slashes at the beginning of the line. This makes the compiler ignore whatever comes after it. This is entirely just text that is not run on the Arduino. It never even makes it to the Arduino. It doesn't take up any space in the Arduino's memory. It is entirely for you, the programmer, and for programmers that come after you to understand what the program does. So I'm just arbitrarily going to say that this is a program to flash an LED and print the number of flashes. At the end of this line, this variable, we can tell ourselves, remind ourselves, or tell other people what loop count actually is. Although it's pretty self-explanatory, when you look through the program, you can, declare an integer to count number of flashes. Initialize serial communications at 115 to 100 baud. LED on pin 11. 12. Set pin 12 high. Or you can turn on LED. Or you can just leave that blank because it doesn't really deserve a comment, I think. Wait X milliseconds. And you can embellish this any way you see fit. Whatever makes sense to you as the programmer, and whatever makes sense to programmers that may come after you, looking at your program and trying to understand what it does. But for now, I'm just going to start this, make sure that there's no mistakes. There are no mistakes. All changes are saved. Go back to a project space. And again, if you wanted to save this and build up from it, you could duplicate it, or you can just simply keep it there and come back to it later. Alright, so we've done a few things that are interesting, but not terribly useful. Let's get going with something a little more useful and heading towards a positioning application like an elevator. So first off, when you're staring at these two versions of a program, except for the fact that this was changed by me a minute ago, and this was changed by me yesterday. The title and the picture really don't tell you much. So let's modify this a little bit. We'll click into one of them and check out what's in the code. And this is the empty code. This is just the circuit built on the breadboard. So let's change the name to circuit no code. And go back. And this one is what we just finished. So again, we're going to change this to pink LED and count blinks. And although that text does actually completely fit in the block, I'm just going to put it in the actual description as well. We're going to start off with this, but we're not going to make any more modifications to it until we duplicate it. Copy of blink LED and count blinks, so we know we're not blowing away the original when we save this. So what's the intent here? My intent here is, rather than simply count the number of times an LED blinks, we're going to use the LED as a status. And we're going to use a number that changes and keeps track of some value. And that value is going to change based on the state of the push button. So let's now change the comments to reflect what we're going to do. And that'll help us keep track of what we are moving towards. So I think what we're going to do is, when push button is pressed, count up until the maximum value is reached, and turn on LED. When push button is released, count down to 0 and turn off LED. Our variable loop count can now represent position. For now, we can just blow away these two lines. And we'll leave this, but make some space for the new code. We also need to detect an actual push button. So in setup, because we are configuring one of the I/O, we'll add another pin mode statement. The push button is connected to pin 11. And we are using the input with the pull-up resistor enabled. We've already initialized the variable position to be 0. I'm actually going to call 0 the bottom of the elevator shaft, which perhaps is a maintenance position, and the ground floor is going to be 1. So we're actually going to count down to 1. For now, we're just going to call this push button the up push button. Now, when we get to the point of making our elevator, we're going to do some planning on paper. We're not going to shoot from the hip. We're going to actually plan the attack of the elevator program a little bit. What is helpful if you're doing something like this, when you're just winging it, as I am, is a little bit of what's called pseudocode. Pseudocode is using commentary in your program to describe how to get the thing that you want to do done. It's not code. It's not recognizable as code. It is human readable. It's not essays. It's not even full sentences necessarily, unless a full sentence makes sense. It's just short form text descriptions of what you're going to do that makes sense to you, the programmer. So what would make sense in this case? Well, step 1 obviously is check push button. Step 2 would be to make a decision based on what the state of the push button is. So if push button is pressed, add 1 to position. On the other hand, if push button not pressed, subtract 1. We want to keep track of position, so we're going to print position to serial console. And finally, with the LED state, we want to turn on LED if position is greater than or equal to, let's call it top floor. Also, if we're at the top floor, print floor 4. At ground, print ground floor. So let's make this and see if we made any mistakes. So what's the first step? Check push button state. So the first thing that we need is a container to hold the push button state. Since the push button state is just on or off, it's a logic variable. It's never going to be 2 or 3 or 10. We can use a Boolean variable type. We can call this push button state. We can initialize it, but we don't really need to, since before using the push button state, we are going to be checking the push button state. We're going to assign the variable push button state whatever is returned by the function digital read, capital R. And since we're not writing a state, we're reading a state, we don't need 2 parameters to be passed to this function. We only need to tell it what pin we're asking the function to look at and report back to us. So in this case, it's pin 11. Step 2. If push button is pressed, add 1 to position. So now we're making decisions, and we're getting into what are called conditionals. The most basic conditional that you're going to run into is the if, then, else statement. If this is true, then do this. If it's not true, you can check for another condition or a third condition or a fourth condition. And then finally, if all else fails, else, do this. We're going to keep this simple, and we're going to keep it all isolated in this so that it's extremely clear and extremely easy to read. But later on, when we're doing the full elevator workup, I'll introduce you to some shortcuts. For now, if, and in brackets, we put the condition the decision is being made upon. So the decision is if the push button is pressed. If the push button is pressed, we're expecting PB state to come back as true, or 1, or high. Those are all 3 valid options. But we're going to start off with high, because when we're controlling the digital output, we use high and we use low. So when we're reading the input, we're also going to use high and low initially to keep everything very clear. If push button is pressed, then we expect PB state to return a high. If PB state equals high, then do something. So 2 new things. In C, a single equals is an assignment. In this command, we are assigning the value of digital read pin 11 to PB state. In the initial creation of this variable, we are assigning the variable position a value of 0. So in this code right now, if we were to run it, PB state is initially assigned the value of pin 11, high or low. If I left this exactly as it is right now, then high would be assigned to PB state. It would overwrite PB state, and regardless of whether the push button was actually pushed or not, when it got to this deciding point, high would be assigned to PB state, and because it was high or true or 1, it would execute the code, which means it would execute the code all the time. In C, and a number of other languages, to compare 2 values, you use a double equals. That's going to trip you up a lot until you get used to it. It's very frustrating, and even after years and years and years of programming, you will, just being human, make this mistake. Now, if this is true, it's going to execute the command that follows. In this case, we're only doing one thing. We are incrementing position by 1. And we could just simply leave it at that. But if you were checking the state of the push button and you wanted multiple commands to be executed if push button is high, then the way to do that is not with multiple if statements with a single command. It would be to add curly braces. These curly braces can hold any number of additional instructions. So we could increment the position, we could check the value to make sure that it isn't getting too high, we could automatically print out the value, but only if the push button was high, just by using the curly braces to contain all of the different things that we want to do if the push button is pressed. We don't have to in this case, but for the moment, again, just to keep everything standard and clear and flexible for when we inevitably have to make changes, I'm going to put everything in curly braces as if it's multiple commands. Step 3. If push button is not pressed, subtract 1 from position. I'm going to be lazy or efficient, depending on how you want to look at it, and copy this text, paste it down here, and just change what's relevant. So if the push button state is low, I want to subtract 1. Next up, let's print the position to the serial console. Using print lines so that each number comes up on its own line. If position is greater than or equal to the top floor, now we turn on the LED. At this point, there's 2 things that we need to do. 1, how do we define top floor? Are we going to make the top floor the floor number, the floor 4? Are we going to be a little more fine-grained and measure the position? Say the top floor is 40 feet above ground level. This is not too important right now, but it will be important later, because later on when I do my elevator, I don't simply want the floor to magically change from 3 to 4 1.5 seconds later. I want to do some limited simulation of a physical reality. So mine is probably going to be something like a floating point number, where I can be at floor 1.0, 1.1, 1.2, 1.9, and then arrive at floor 2. Or I may decide to use the height above the ground, measured in feet, measured in meters. I'm not really sure right now. But for the moment, we're going to consider the top floor to be floor 4, so it'll be an integer. We'll just use whole numbers and delays to simplify this for now. We still need to define what the top floor is. So up here, where we are declaring our variables, although the top floor is not needing to be a variable, because my program is obviously not going to, in real time, change what is considered the top floor. It's really going to be a constant. I am, for this, still going to maintain some consistency and make the top floor be an integer. And the top floor is going to be equal to 4. And while we're at it, let's also define at least one other position, which is going to be lobby. And that's going to be equal to 1. So now we can go down and make the comparison. If position is equal to top floor, then do what's inside the curly braces. What we're going to do in the curly braces is turn on the LED. The LED is connected to pin 12, and we're setting it high. Now, since the next pseudocode is, when we're at the top floor, also print floor 4, we can actually combine these 2 steps. Serial library, print with a line feed after it, floor 4. On the other hand, if we're at the ground floor, which we are now going to call lobby, we'll again just copy this code, paste it here, and change what's appropriate. So if the position is now equal to lobby, we're going to turn off the LED and print. Oh, just realized I missed the quote for floor 4. For now, I'm going to complete this program and I'm going to get rid of this code, except for the delay. But because I don't want the delay to be there right now, I don't want the delay to be executed, I'm going to put 2 slashes in front of it, which comments it out, and it becomes text that the Arduino will ignore. So at the moment, within the loop, there are no actual delays. It just reads the push button state. If the push button is pressed, well, let's back up, because I want to be clear on this. We've defined the top floor as being equal to 4. We've defined the lobby as equal to 1. Our initial position is the maintenance position, or lockdown, or whatever. We're starting off at floor 0. We're creating a Boolean variable that can hold the push button state. Then we go on to setup, which is the code that executes once. At the beginning of the program, we initialize the serial communications. We tell the Arduino that pin 12 is an output. We tell the Arduino that pin 11 is an input, and that we want the pull up to 5 volts resistor to be connected. Once those 3 lines are done executing, setup is done, execution moves to loop. We right off the bat check the push button, so that push button state is now something valid, since we did not initially declare the push button state to be anything. If the push button state is high, you'll notice that I didn't say pressed. If the push button state is high, meaning there's 5 volts at pin 11, then the position is going to be incremented by 1. If the push button state, on the other hand, is low, which means that pin 11 sees 0 volts, then we're going to subtract 1 from the position variable. We will continuously print whatever the position value is. If the position is equal to top floor, which at the moment is the same as saying, is position equal to 4? Then we're going to turn on the LED and we're going to print floor 4. If the position value is equal to lobby, which is equal to 1 right now, then we will turn off the LED and print at lobby. There are a number of mistakes in this program. This is not going to work the way I'm intending it yet, but it will be illustrative when you see what it actually does. So we'll start the simulation and we'll see what happens. And immediately the LED is on, which all by itself is curious because the LED shouldn't be on until it's at floor 4, and if we're starting from floor 0 and we're not pushing the push button, why is the LED already on? Well, let's take a look at the serial console and see what's actually happening. 1800. That's an awful lot more than 4. So the number one thing that we know is that it's counting up and it's not stopping at 4. The number two thing that we know is that it's counting up even though we haven't pushed the push button, which is the condition for counting up. So let's stop the simulation and briefly start and stop the simulation. So in the time that it took me to start and stop the simulation, it did count up to 15. And if we scroll back through the output of this program, we can see that it was at some point at the lobby, because the lobby is floor 1, and then it was at floor 2, floor 3, floor 4, printed floor 4, and continued flying past floor 4 to be 5, 6, 7, 8, 16,000. So let's take a look at what's wrong with the program. The first issue is the wiring change that we had to do earlier. Because there is no pull down resistor and we had to do the pull up resistor, then when the push button isn't pressed, the input is 5 volts, which is high. And when it is pressed, it's low. And that's the exact opposite of what we were initially expecting. One really easy way to change this without changing any other code is, since we know that pushing the push button is going to give us a 0 and releasing the push button is going to give us a 1, we can use the NOT operator to invert the state of the push button when we read it. In the Arduino, you can invert a bit just simply by putting an exclamation in front of whatever it is. So push button state is going to be equal to not digital read 11. If digital read 11 returns a 0, then the not operator will assign a 1 to PB state. If it returns a 1, it'll be inverted by the exclamation mark, and PB state will be a 0. So without changing anything else, let's start the simulation and watch the output. Now at least it's counting down. And as expected, once you hit 0 and you count down by 1, it goes negative. Now, one very interesting question is, how big or small can these wrong numbers get before they roll over? That depends on the data type you use, and I'm not going to go into detail on the data types and binary and such just yet. For now, we just want to correct this so that it does what we expect. And as long as we're here, watching these numbers continue to go negative, 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 let's push the button and see if they start going positive. And they do. Now, if you wanted to, you could also plot this. So if you go down to the little squiggle trace here and click that, then you will get an active plot of the numbers that are coming out to the serial monitor. If I push the button, the numbers start going up. If I release the button, the numbers start going down. So at least that's working right. The two main ways that I would limit this is either to use a logical AND operation in the conditional that prevents the loop from even running if we are already above our maximum, or a handy function called constrain. So let's start off with the logic, and we'll use the logical condition in the case of pushing the push button to try and increase the number, but we'll use constrain to limit the low. So in the conditional here, we can check to see if, and I'm going to use brackets around the individual sections because parentheses just makes everything very clean and obvious what's related to what. So I'm going to put brackets around this portion of the conditional, which is checking to see if the button is pressed or not. But if the button is pressed and current position is less than top floor, then we will allow it to increase by 1. In the second case, we can let this loop, this if-then statement, execute as long as the push button is being pressed. But instead of just taking position and making it equal to 1 less the position, and then later on checking to see if it's too low, we can put it inside a function called constrain. So if we go to the Arduino reference, and we go to the documentation, and we go to reference, this is the main reference page for all of the commands that are available to you without including any additional libraries at all. This is included with every program you write by default. And we're interested in the math function constrain. Constrain takes x, which can be a function, and compares it to a and b. A is your minimum, b is your maximum. If the number returned by this function is less than a, then constrain will return a to our program. If it's greater than b, it'll return b to the program. So in our case, if the push button is not being pressed, position equals constrain position minus 1 is the function, and the minimum that we want it to return is a 1, and the maximum we want it to return is a 4. But we can also use the fact that we may change this later. So now if the push button is low because it's not pressed, position is going to be equal to position minus 1 fed into the function constrain. And if it's less than 1, position will be 1. If it's greater than top floor, which it won't be because we're not adding, it would be returned as top floor as well. So now let's test it. So now the program is writing out a continuous 1 at lobby, 1 at lobby, 1 at lobby, which is realistically expected because we're not preventing it from printing multiple statuses. We're only preventing the position from decreasing. If we push the push button, now we're at floor 4. And that happened extremely fast. When I say extremely fast, I'm talking relative to a program with a delay. Realistically, this browser is, as you saw earlier, it was running through the program about 1,000 times in 20 seconds, which is actually ridiculously slow compared to the hardware. But let's add a delay. So we're just going to uncomment this delay, which will return it to its function as an actual command. And if we simulate with that, now what do we get? If I push the button, we're at floor 4. If I release the button, we're at the lobby. So at this point, we have an interesting program that is working. There's no errors. It's a little derpy, but it's a good starting point. So I'm going to make a change to the name, because it's no longer blinking an LED and counting blinks. It is derpy elevator sim. And I'm going to go back to the project manager, make a duplicate, which will open the copy. And then I can make all the changes that I want to that without fear of accidentally losing where we are. I'm also going to make a modification of the orientation of all this. Since this blue LED in theory is floor 4, and it's going to be floor 3, 2, 1, maybe that maintenance position down here if I really get desperate. It would be nice if this board and the Arduino were vertical. So I can select the breadboard and rotate the breadboard. And I can select the Arduino and rotate the Arduino. And then zoom to fit. Now let's quickly duplicate the LED and the push button and the code in such a way that we actually have something somewhat elevator-like to look at. Since I've already gone through the step-by-step construction of the first LED and push button and resistor and the wiring, I'm going to rapidly go through the other three. I believe I got everything right, so let's make a few tests. Code. Initially, I'm not going to pay attention to these three push buttons. We're still going to only function off of this push button. And when we push it, it's going to climb up towards floor 4, which is the blue. And when we release it, it's going to climb down towards floor 1, which is green. So the only thing I'm really caring about initially is configuring these LEDs, those pins, as outputs. And when it's at floor 3, 2, and 1, lighting up those LEDs. The description of our program is about to change. So when the push button is pressed, count up until a maximum value is reached and turn on LED. When PB is pressed, raise elevator to floor 4, lighting each intermediate floor position along the way. When PB is released, lower our elevator to floor 1, lighting each intermediate floor position along the way. Now, as our program starts to get more complicated, we should also simplify it in certain ways. One of the things that will be confusing if we leave these as just numbers, pin 12 and pin 11, is keeping track of which pin is which. You can always look at your breadboard when you need to know what is connected to what, but an easier way, since these things are things that will not change frequently, if at all, is we can take advantage of pound define. Now pound define does something really simple and really handy. It allows us at the beginning of a program to define a label that will be automatically converted when the program is sent to the Arduino to something else. So what would make sense here? Well, what makes sense here to me is a hierarchical description of what the pins do. So we're going to define pin floor 4. If this was a variable, we'd put an equals sign here, but it's not a variable. This is just something, it's not even a constant. It takes up no space in the processor at all. It is entirely something that, it's like a lookup table to the compiler. So when it sees the text, pin floor 4, it will convert that instance everywhere in our program to something else, 12. But there's two things that are going to be associated with floor 4 that are connected to pins on the Arduino. So pin floor 4 LED is 12, and the pin floor 4 push button is 11. So now we can take this and we can just go through the program, which is currently short enough that we can do this manually, but in the Arduino IDE you would want to use the search and replace function. As far as I know, the simulator here doesn't have an easy text replace function, so we're just going to replace pin mode 12 output. Well, what the heck is connected to pin 12? With, oh, okay, pin floor 4 connected to the LED. Oh, okay, so the LED for floor 4 is connected to pin 12. And it's an output. And pin floor 4 push button on 11 is an input with the pull up. When we read it, we're not digitally reading and inverting pin 11 now, we are reading floor 4 push button. Now this does two things. One, it makes the program much more readable, because when we get to this code, if we're reviewing the code, or if someone who comes after us is looking at this code trying to figure out what it does, they don't have to deal with seeing a 12 here and figuring out what 12 is. They can just read the text and it'll make sense. The second thing is, let's say later on we decide to change what pin the floor 4 LED is connected to. If we're not using a define at the beginning of the program like this, then let's say we damage pin 12, and we just simply want to move pin 12 to a free pin like pin 4. We can do that just by changing one wire in the real world. But in the program, we would have to search through the entire program looking for every instance of 12. Check it to make sure that the 12 is actually referring to a pin and not just a 12 from a variable or a 12 in text, and then replace it. In this case, if we were to move the floor 4 LED from pin 12 to pin 4, we'd literally just have to do that and send the program back out to the Arduino again. And it takes care of everything. So let's grab that line, duplicate it 3 times, and correct only where necessary. So pin for floor 3, floor 2, floor 1, and this is the only time we're actually going to have to look at the wiring and verify that yes, floor 3 LED is connected to 10 and 8 and 6. 10, 8, 6. And while we're at it, let's also, because we will be doing this, duplicate the pin references for the push buttons. And at the moment, they're all in order. So 12, 11, 10, 9, 7, pin 5. To light up the LEDs, we have to declare them as outputs. So in setup, floor 3, floor 2, floor 1. Ten, 8, 6. Now, an interesting point of note is that digital write to a pin is permanent until you write something else. So you do not have to continuously write high to the floor 4 LED to keep it high. If we quickly do a simulation and we watch the LED, the blue LED for floor 4, you will see when I push the push button to go up, the LED doesn't turn on until we're at floor 4. Aha, okay. I forgot to update. I updated the pin, but I also forgot to update the description when I copied it. 3, 2, 1. So unfortunately it was looking for the push button on pin 5 once I accidentally redefined pin floor 4 push button to be pin 5 here. So it will work now. So we're at lobby, we're at floor 4, we're at floor 1, and it's printing 1 at lobby to the serial. If I press the button, it will be about 4 seconds before it reaches floor 4. The LED will turn on. But you'll notice that when I let go of the push button, the LED doesn't turn off until it gets to lobby. That is because when it's at floor 4, this becomes true and it writes a high to the floor 4 LED. But at floor 3 and 2, there is no code. This isn't being executed. So it's not writing a high, it's maintaining the high that was written until the mode is changed to low at the lobby. So this code has to change a little bit because we want the LED to turn off as soon as it's not at floor 4. Well, top floor. While I should change this, I'm not going to yet. This is something that you can do on your own. But we will definitely change this in the final program. So when we're at floor 4, we turn on the LED. But at any other floor, except for lobby, where we turn off the LED, nothing happens. So we're going to make a slight modification, and we're going to add an alternative. So if you go to the Arduino reference for if, you'll also find a reference for else. Now, you can have any number of else ifs in the middle, and definitely you should read this and play with it yourself, but you can have a first if then do this, and this is the only thing that you necessarily need. If this is not true, then you can check for additional conditions to be true. But if none of these are true, else do this. This is your catch-all for anything that is not caught by these. So in the case of the elevator, I'm going to keep this simple again, and else, curly braces, so if position is equal to the top floor, print top floor and turn on the LED. Otherwise, turn off the LED. If we're at the lobby, we are going to turn on floor 1 LED, but if we're not at the lobby, turn off the LED. And with the two intermediate floors, we're not going to bother printing anything right now. We're just going to turn on the LED or turn it off if it's not at floor 3. And the same at floor 2. And simulate. And we have our first error. So, reading down here in function void loop, LED was not declared in this scope. That is correct. LED is not a variable or a constant or a declaration. Not LED, it's low. And a quick scan of the other code. Looks like that is the only mistake that I made, so let's try it again. Sweet. And the green LED is on. Open the serial monitor. We are at lobby. And push the push button to go up. And release the push button to go down. This is as far as I'm going to go with this video for now. It's quite long, and I'm going to end it here. But we're going to continue this in part 3. My recommendation to you at this point would be to play with this code, make a duplicate, copy it, and take what you've learned and experiment. It's a simulation. You can't break anything. And you can always come back to your original if you make a copy. So I'm going to rename this because it's not copy of Derpy Elevator Sim. It is less Derpy Elevator Sim. So, have fun, experiment, and I'll see you in section 3.